Okay, let's finish off by taking a look at applying these distributions to understand a certain setting. So it turns out, well, let's take a look at this first example. A casino patron will continue to make $5 bets on red in a roulette until she's won 4 of these bets. On any bet, she either wins $5 with probability 18/38 or loses $5 with probability 20/38. So what's the distribution of x, the number of bets necessary to win 4 bets? So right away in this problem, it's probably worth noting that it seems like that the $5 doesn't have anything to do with it. It's simply a distractor. We want to know the distribution of x, the number of bets she has to place necessary to win a total of 4 times. Okay, so it seems like, first of all, it doesn't fit the geometric distribution because in a geometric distribution, you're waiting until a first win. It also doesn't seem to fit the hypergeometric because the hypergeometric has a collection of items that are split into 2 classes. It does seem to fit the negative binomial situation. So the negative binomial situation is one where we have a sequence of independent trials, each with the same probability of success. And we are waiting until we have our successes, and in this case we're talking about 4 successes. So this distribution would be a negative binomial distribution. It has 2 parameters, r and p, and the parameter r in this case would be 4 because there are 4 successes that we're waiting for, waiting to occur, or accumulating, I guess. And P would be the probability of those successes. So in this case, the probability of a win is the 18/38. So this particular distribution is a negative binomial with parameters R 4 and P 18/38. That's all you need to know. You can plug that in then to the formula that we derived earlier or that we introduced earlier and find the probability of any one of those values of X, which range from 4 to infinity. Okay, let's take a look at another one. A large number of insects are expected to be attracted to a certain variety of rose plant. A commercial insecticide is advertised as being 99% effective. Let's suppose that 2,000 insects infest a rose garden where the insecticide has been applied, and let X be the number of surviving insects. What's the distribution of X? Okay, well, here we could talk a little bit about whether or not the previous 3 apply. So let's first talk about whether this would be the case of a geometric random variable, and it seems like it's not. It seems like we've got 2,000 insects, so there's 2,000 trials, and we're applying the insecticide to see if how many survive. So we can kind of think about this thing as 90. It's definitely not waiting for a first success kind of a thing. That's what we expect from a geometric random variable. And since it's not geometric, it would definitely not be negative binomial either, because negative binomial waits until we accumulate a certain number of successes. And the hypergeometric doesn't seem to fit here either. So it seems like it's not a hypergeometric either, because hypergeometric takes a certain collection and splits it into 2 classes, and we're not told anything about the insects being in 2 different classes. So it's not a hypergeometric distribution either. So if we go back to the previous 3 distributions we've studied, that would be the Bernoulli, the binomial, and the Poisson, we can definitely see some fits there. So it's not a Bernoulli random variable because it's not a single trial. We can kind of think of it as 2,000 trials because each insect is in effect a trial. So it seems like it's a sequence of Bernoulli random trials, or sequence of Bernoulli trials, 2,000 of them. So and that seems to lead us to the conclusion that this could be modeled by a binomial random variable. Let's just think about the requirements for binomial random variables. You have a sequence of Bernoulli trials where the probability of success is fixed, and so I guess And we're told the insecticide's 99% effective, so each of these 2,000 insects is being kind of tested or trialed with the insecticide. So yeah, we could say the probability is fixed. The probability that one of these insects, I guess, survives is 0.01, and it's fixed. And we could argue, I guess, that each insect is its survival is independent of another insect's survival, um, and there's a fixed number of trials, 2,000 of them. So indeed, this could be modeled by a binomial random variable then, and in that case, the number of trials would be 2,000 because we have 2,000 insects, and then the other parameter involved in the binomial random variable is the probability of a success, and a success here is a survival. So I guess we have a 1% survival rate. So success would be 0.01 as the probability in this particular situation. So binomial random variable, n equal to 2,000, probability of success equal to 0.01. Now, noticing that this has this binomial random variable opens the door to Poisson approximations. So you could use a Poisson to perhaps approximate this variable, but the distribution itself, in an exact sense, would be best modeled by a binomial random variable. Okay, let's look at the last one and end here. So suppose I wish to select a committee of size 3 from this class, so our class, and suppose the class has 28 men and 9 women. Let X be the number of men selected. If selection is random, what's the distribution of X? So let's go back to the three random variables we looked at in this chapter. Is this a geometric distribution? Well, it's certainly not, because a geometric distribution waits until a first, I guess, success occurs. It doesn't seem like we're waiting until the first success in this situation. So it's not geometric. It's not negative binomial either, because again, we're now accumulating successes. This does seem to fit the hypergeometric, though. It's similar to drawing aces from a deck. We have a finite number of people in a collection, so we have 28 men, 9 women, so a total of 37 in the collection, and they're split into two classes, men and women, and we want to count the number of, say, type 1 people selected when we take 3 from the class, and the type 1 in this case is men. So indeed, this does seem to fit the hypergeometric situation. So let's identify the parameters then. We have the parameters in the hypergeometric are big N, and little m. So let's see, big N is the size of the collection. It would be 28 plus 9, or 37. So that would tell me the size of the population, or size of the collection. So big N is 37. Let's see, little n is the size of the selection that we're taking out of the collection, so that little n is 3 in this case. So we're taking 3 men out, or I should say 3 individuals out of the class to serve on a committee. And then the last thing is little m, and little m is the number of type 1 objects in the collection, where we're counting how many of those appear in the sample. And in this case, that's contextualized as men, so little m would be 28. And that would completely specify the distribution here, which would allow us then to calculate all its probabilities. Okay, that concludes the lecture on this material. I wish you luck on your homework, and have a good spring break, everyone.